In section 2.1, we're going to go back to the idea of congruence that you discussed in Math 223, right after you did divisibility. And then we'll have to add in an extra idea that you didn't do in that class. So the first definition says, suppose a, b, and n are integers, and assume n is greater than 0. Then we say the two numbers a and b are congruent, so a is congruent to b modulo n if n divides a minus b, if n divides their difference. Okay, so n's fixed, and then you're saying, what does it mean for a to be congruent to b? N divides their difference. So notice order matters here. A minus b, right, is not the same as b minus a. So if in this definition, if you say a is congruent to b, a is here and b is here. And the notation, if they are congruent, we write a is congruent to with 3 lines, not an equal sign. A is congruent to b mod n. So instead of saying modulo, you can just say mod. Okay, so perhaps you remember this definition from discrete math. As an example, it says, let a be 6 and n be 5, okay. Find several values for b such that a is congruent to b mod n. So just to play with the definition, here's an a, here's an n, and the question is find b's for which this is true. Okay, so what I'm looking for is I want 6 to be congruent to b mod n here, which is 5. Well, let's go to the definition. What does the definition say this means? This means 5 would have to divide 6 minus b. So in other words, if 5 divides 6 minus b has to be a multiple of 5. So what could b be? So b could be 1, because then 5 would divide 5. B could be -4, couldn't it? Right, because 6 minus -4 would be 10, and 5 divides 10. What's one more? If I want to get a 15 here, b is going to have to be -9, wouldn't it? Because then 6 minus -9 would be 15, and 5 divides 15. B could be 6 too, couldn't it? Because then 6 minus 6 would be 0, and 5 divides 0. Okay, so there's some values there just to get a feeling for what's going on. Notice I changed the mod definition to divisibility and thought of it that way. That's exactly what you did in discrete math. All the proofs that involve mod, you wrote in terms of divisibility. And in fact, in terms of divisibility, you wrote in terms of an equation. One comment though, they say let n be at least 0, so n could be 1. But that's kind of silly to let n be 1, because if n is 1, 1 will divide everything. So if n's allowed to be 1, every a is going to be congruent to every b, because 1 will divide the difference. So oftentimes, in practice, we want n to be at least 1. I don't know why you would, n to be at least 2. Right? N's greater than 2. I don't know why you would ever consider n to be 1, because everything is related to everything, and it's not very, everything is congruent to everything. It's not very interesting. Okay, so when I say do congruence, I'm never going to pick n to be 1. That's just kind of silly. Okay, let's look at theorem 2.1. It says let n be a positive integer. So again, they're allowing it to be 1, which is silly. For all integers, for all a, b, and c, and z, we have the 3 following facts. A is congruent to a mod n. If a is congruent to b mod n, then b is congruent to a mod n. I know some of these sound silly, but whenever you learn a new idea in mathematics, you can't necessarily assume that all properties you had before for other things naturally carry over. You have to check them. And then the third condition, if a is congruent to b mod n, and b is congruent to c mod n, then a is congruent to c mod n. So if a is to b and b is to c, then a is to c. Okay, so I mean, the property 1 is called the reflexive property. A is related to itself, it's congruent to itself. Again, that's the reflexive property. 2 is called the symmetric property. If a is congruent to b, then b is congruent to a. So if one thing is related to the second thing, the second's related to the first. And the third is called the transitive property, the transitivity. because if one thing is related to a second and the second's related to a third, then the first is related to the third. That's in general what transitivity means in mathematics. Okay, well, let's just play with these for a second. I don't think we need to prove the first two. Let's just explain why that would be true. Right? So why would, you pick your favorite integer a, why would a have to be congruent to a mod n? Okay, well, what was the definition? Remember, n divides a minus b, right? But here we want a and b are the same. It's really a, not b. And that's going to be true. N's going to divide 0. Okay, so n divides 0, and so a is congruent. Congruent to itself. That's no big deal. Okay, now what about the second condition? Suppose a was congruent to b mod n, so n divides a minus b. Right? That's what our assumption is. Right? Well, what would that mean? Well, if n divides a minus b, that means a minus b is some kn for some integer k. That's the definition of divisibility. But if I multiply both sides by -1, I'll get b minus a is minus k n. Right? Multiply both sides by -1, a minus b becomes b minus a. But what does this mean? Right? This gives me n divides b minus a, doesn't it? Because I have an integer times n is b minus a. But if n divides b minus a, that means b is congruent to a mod n. Okay. Okay. So those are, don't take that much work. Again, I just gave you the idea of the proof. You have to write that up nicely with some words. But let's actually prove the third one here. Okay, so let's assume A is congruent to B mod n, and B is congruent to C mod n. There's my assumption. Okay, then, well, what is the definition of mod? That means n divides A minus B, and n divides B minus C. That's a definition. Again, in a proof, you don't do 8 things in one step. Okay, well, let's go back to my definition of divisibility. So, if n divides A minus B is some k1n. And if n divides b minus c, then b minus c is some k2n for some k1, k2, n, z. That's definition of divisibility. So all I've done so far, I used definition of mod and definition of divisibility. Again, this should sound familiar from Math 223. All right, so now I'm going to stop and think about what I'm trying to get to. I'm trying to get to A is congruent to C mod n. Okay, so let me do scratch work over here and work backwards. I want A congruent to C mod n. Well, what would that mean? I need n to divide A minus C. Well, what does that mean? That means A minus C is something times n, where the something's an integer. Okay, so I'm kind of working backwards here. Right? Well, notice I need A minus C, right? I need A minus C. Okay, hence A minus C equals, well, if you just kind of go with your gut, how can you get A minus C from what I have? Isn't that A minus B plus B minus C? Because the B's drop out. Again, why did I do that? Because of here. Now, you could have solve for A here, solve for C here, and then just put them in for A and C and simplify. You'll get the same thing. I'm just saving a step by doing it this way. Now let me continue. Equals A minus B is K1n, and B minus C is K2n, which is K1 plus K2n. And K1 and K2 are integers, so we know their sum is an integer. So therefore, I have n divides A minus C. Right? I have A minus C is an integer times n. And A is congruent to C mod n. And there's my proof. There's one little black square to indicate the end of the proof. Right? notice I didn't jump from here to the mod, right? Because that's not the definition of mod, right? I went from equations to divisibility to mod. Notice here I went mod to divisibility to equations. Did stuff with equations, then went to divisibility to mod. That's typically the way the mod proofs go. Go from mod to divisibility to equations, do stuff with equations, go back to divisibility, then go back to mod. Okay, so every number is congruent to itself mod n. If you don't have to be careful about order, right? I mentioned in the definition, the A is first, so it has to be A minus B. This theorem tells you don't have to be that careful, right? Because if A is congruent to B, B is congruent to A. So you don't have to be careful about which way you write it in the definition. And then 3 is the transitivity. Okay, well that wasn't too bad. Okay, let's see what's next. That was that. Okay. Theorem 2.2 says, I'm not running all the assumptions with A, B, and N, but if A is congruent to B mod N, and C is congruent to D mod N, then A plus C is congruent to B plus D mod N, and also AC is congruent to BD mod N. Interesting, okay. Okay. So I want to do these proofs as well, even though the additional one kind of has the flavor of the one we just did. But let's think about what this theorem is saying. So if A and B are equivalent, or congruent mod n, and C and D are congruent mod n, if I take this A, the A plus the C here will be the same as the B plus the D here mod n. So if two things are congruent mod n and two things are congruent mod n, right? If you add any two of them, A plus C, it's the same as adding B plus D. In other words, you don't have to be careful which ones you add. Same thing for multiplication. So if these two are the same mod n and these two are the same mod n, then that times that is that times that. Okay, so let's do the proof here of the first one. Well, let me assume the if and do some work, preliminary work, before we get into the each one. So let's assume A is congruent to B mod n, and C is congruent to D mod n. Well, definition says then n divides A minus B, and n divides C minus D. That's the definition of mod. And now let me go to equations. So if n divides A minus B is some k1n, and C minus D is k2n for some k1, k2, nz. So it's just like the last one. So this is the no thinking part, right? I wrote down the assumption. I went from mod to divisibility, then divisibility to equations. That's the same sort of thing you do in a lot of these. Okay, so we kind of need that for both, I presume. Okay, so now what are we interested in? Well, let's focus on this one here, the sum, and I'm going to work backwards like I did before. So I need A plus C to be B plus D mod n. Well, what would that mean? That means n divides A plus C minus B plus D. That's what I need. Or what does that mean? That means A plus C minus B plus D is something times n. That's what I have to get to. So if I can get this, that means this, which would mean this, and I'm finished. Okay. Well, how can you get an A plus C? Now this is the same thing as minus B minus D. So I need A plus C minus B minus D. Well, A plus C minus B minus D. If I just add these two together, that's what I get. So it looks like it has the same flavor as the last one, okay? I'm going to start a new paragraph because this paragraph I'm using for both. Thus, let me write that down. A plus C minus B plus D. And again, why am I writing in this form? Because I'm trying to make it look like, that's what it needs to look like to get to the last step. That's the same thing as A minus B plus C minus D, isn't it? Now, why did I rearrange? Because I'm trying to make it look like that now. It is the same thing. That's A minus B plus C minus D. And now when I substitute, I get K1n plus K2n is K1 plus K2n. So it's just like we did on the last proof. Okay? Hence, I have A plus B minus, A plus C minus B plus D is an integer. We know K1 and K2 are integers, so K1 plus K2 is an integer, n. So n divides A plus C minus B plus D. That's what we showed in the previous step. And by definition of mod, this says A plus C is congruent to B plus D mod. So that's the first part. Check. We got this done. Okay, let me erase this, and I'm going to write here, let me just get rid of all that too. Okay, I need AC equals BD mod n. Okay, so we need to get to AC is BD mod n. That's what I'm trying to get to now, using our same assumptions here. So this whole first paragraph is still fine. So what would that mean? I need n to divide AC minus BD. So I need AC minus BD to be something, an integer times n. Okay. Now, this one's not as obvious as the last one. Remember before, I needed A plus C minus B plus D to be something times n. And it was clear how to get this from here. You just added those two things together. Right? How are you supposed to get an AC minus BD out of this mess? Right? You get A minus B times C minus D, you'd have to FOIL that out. That's not going to be AC minus BT. AC minus BD. Okay? So I'm going to start a third paragraph here, but I'm going to erase this to give me some room. Okay? Now, I only needed this in the proof we just did, but to do this proof, I think I need to do some more to this. Okay? So we had first paragraph, second paragraph. I'm starting the third paragraph. I'm going to come back and refer to this. So from the first paragraph above, we get, I'm going to solve for A and solve for C, because then I'll have AC. And we'll worry about the BD later. From the first, we get, so if I solve for A here, A is B plus K1n, isn't it? If you add B to both sides. And C is add D to both sides, you get D plus K2n. Again, the reason why I'm doing that is because I need to get A times C, and it's not, you can't get AC out of what I have here. So I'm solving for A and solving for C. Now I know what AC is, at least. Okay, so I solve for A. I didn't have to do that on the last one because it was easy to get A plus C minus B plus D out of what we had. But this one's different. Okay, thus, now I'm interested in AC minus BD. So that's going to be my next expression. AC minus BD is, well, here's A, B plus K1n, and C is D plus K2n, and I still have minus BD. Now you may ask yourself, well, why didn't I solve for B and D here and then put those in here, for B and D? Well, you could, but it's unnecessary. In fact, you may just come back to AC minus BD. But notice what I have here. There's a BD, and it's going to subtract out, so you don't have to worry about it. Okay? So that's why, I've done this problem before. So I knew I didn't need to do that, solve for B and D and plug in. There's B and D. It's going to subtract out, so it's not an issue. Okay, so let me continue here. Equals, so I'm continuing from here, equals. So if you FOIL that out, you get BD plus b k2n plus d k1n minus bd. bd plus b k2n plus d k1n, oops, I didn't finish, plus k1 k2 n squared minus bd. There we go. Notice, like I said, the bd subtract out, that's wonderful, that's what we need. And then equals, so notice this has an n, this has an n, that has an n in it, so I can factor the n out. So I get b k2 plus d k1 plus k1 k2 n times n. So the bd's are gone. Factor the n out of here, factor the n out of here, factor an n out of the n squared. Okay. And again, all of these quantities are integers, so everything in the parentheses is an integer. And notice what I have. It follows that n divides, right? I have AC minus BD is integer times n, so n divides AC minus BD, and by definition, AC is congruent to BD mod n, and there's my proof. That one took a little work. Okay, so there's our proof. So we'll be using these two facts later. Okay, the next definition. Again, I'm not going to write all of the assumptions, but the congruence class of A modulo n denoted bracket A is the set of all integers congruent to A modulo n. Okay, so you pick your favorite integer A. When you write bracket A, that's a set now. It's the set of all integers congruent to A modulo n. So when I did that example earlier about find several B's, A was 6 and n was 5, and I said find several B's where A is congruent to B mod n. So all those ones that I found would be in the congruence class of 6. So if you look back at that example, you could say, you know, the congruent class of 6 equals, and you know, some of the numbers, I forgot what they were, 6 and some of the others. Okay. Now there's a whole bunch of it. There's more than what we found. There's an infinite number. But, okay, that's a definition. Sometimes you will see them write congruence class A with a little n, that's the n you're modding by modulo n, because if it's not clear for some reason, they'll put the subscript there to indicate mod n. But typically you know which n you're working in, so you don't have to write that down. Okay. Okay, so now we have another theorem. This is theorem 2.3. It says, okay. A is congruent to C mod n if and only if the equivalence class with A is equal to the equivalence class with C. So this is a nice result. So what does this tell you? If two numbers are congruent mod n, their classes are the same. So everything that's related to A is also everything that's related to C. Okay? So if A and C are congruent to each other, everything that's related to A, everything that's congruent to A is also congruent to C and vice versa. So that's kind of a nice little theorem. Okay, so let's do the proof. So it's an if and only if, so you have to assume A is congruent to C mod N, show the class of A is a class with C, then assume the class with A is a class with C, and then show that A is congruent to C mod N. Okay, so let's assume, I'm going to do the direct way, so let's assume A is congruent to C mod N. Okay, so I'm assuming this. I want to show these two sets are equal. Well, how do you show two sets are equal? You have to show containment both ways. So I need to show anything in this class is in this class, anything in this class is in this class. Okay, so I'm going to pick something in here and show it's in here. Okay, so let B be an element of the equivalence class of A. Well, what does that mean? Right? If B is in the equivalence class of A, that means B is equivalent to, congruent to A, isn't it? Right? So B is congruent to A mod N. That's a definition of congruence class, right? If B is in the congruence class of A, that means it's congruent to A. Okay? But since since A is congruent to C mod N, how do we know that? That's our assumption. Right. We conclude that B is congruent to C mod N. Now why is that? I have B is congruent to A mod N, and A is congruent to C mod N. Why does that make B and C congruent? Well, that's the theorem we just proved. It's that transitivity, that last thing, right? If one thing is related to a second, and a second is related to a third, the first is related to third. So I have the first, B is related to A, and B is congruent to A, and A is congruent to C, so B is congruent to C. So that's by theorem 2.1. Well, if B is congruent to C, doesn't that put B in the equivalence class with C? Hence, B is an element of the class with C. That's a definition, right? The equivalence class with C is everything that's related to C. So if B is I keep saying related, I'm using the generic term relation. Right? So if B is congruent to C, B is in the equivalence class with C. So notice what I have. I picked a B in the class with A, and I showed B was in the class with C. Therefore, the class with A is contained in the class with C. Right? I picked something in the class with A, and I showed it was in the class with C, so we have containment that way. Now the other way works exactly the same, so I'm not going to do that. So a similar argument can be used to show that the class with C is contained in the class with A. It's the exact same argument, you just have to change the letters. Thus, the class with A is the class with C. Okay, so that's, assume this, show that. That's what that is. Okay, the other direction's a lot easier. Remember, it's an if and only if. We've only done one direction. We did the direct implication, now we have to do the converse. So now assume the class with A is the class with C. Okay, so since A is congruent to A mod N by theorem 2.1, That was the reflexive property. We see that A is an element of the class with A, right? A is congruent to itself. And remember, the class with A is everything that's congruent to A. So A is in the class with A, but the class with A is the class with C. Right? So from this fact, we get that A is an element of its own equivalence class, but we assumed that A was the same as the class with C. Well, but if A is in the class with, so A is now an element of the class with C, hence, if A is in the class with C, what does that mean? That means A is congruent to C mod N. Because remember, what does the class with C mean? It's everything that's related to C. If A is in the class, that means they're congruent to one another. And there's our proof. Okay, that took a little bit of work. It wasn't too difficult, but it took a little bit of work. Okay. So again, what does this result say? If two things are if two integers are congruent to one another, their classes are exactly the same. Okay, now as a corollary to this, corollary 2.4, it says two congruence classes modulo n are either disjoint, meaning the intersection is empty, or identical. That's nice. It's a nice result. Yeah. So it tells you if you pick two classes, class with A and class with B, it's one of two things they're at. Either the two classes, the intersection's empty, they have nothing in common, or they're the exact same class. So in terms of Venn diagram, if you have the class with A and the class with B, right? If here's the class with A, the class of B cannot do this. Okay, you can't have a non-empty intersection unless they're the same thing to start with. So, I mean, what is this saying in terms of Venn diagram? Either you have the class with A and the class of B and there's no intersection at all, or you have the class with A and the class with B and they're exactly the same. That's what this corollary is telling us. Okay, this proof is not very long, so we're going to do it. Now, how do you prove an OR statement in general? That's the general procedure. If there's two things, okay, you assume assume that one. So if I'm going to call them the class with A and the class with C, I don't know why. I guess because that's what we were doing here. Right? If the class with A intersect the class of C is the empty set, then we are done, aren't we? Because they're disjoint. Done. So that's what you usually do. You assume it's this, say it's this. If it turns out to be this first case, you're finished. There's nothing to show. You've satisfied the theorem. Right? So now assume it's not this. So assume the class with A intersect the class with C is not the empty set. So if classes are not disjoint, we have to show they're identical. Or you could have done it the other way around, right? Assume the two classes are the same, then you're done. Well, now assume they're not the same, and then show they'd have to be disjoint, whichever. Okay. Then, well, what does this mean? There exists some B in the intersection. Right? What does it mean for a set to be non-empty? There's something in it. Okay, since B is in the class with A, right? B is in the intersection, so it's in both. B is in the class of A. That means B is congruent to A mod N, right? That's what it means for B and, remember, the class of A is everything that's congruent to A, so B and A are congruent. Likewise, same thing. Since B is in the class with C, then what does that mean? That means B is congruent to C mod N. Okay. So B is in both of these. Since B is in the class with A, that means B is congruent to A. B is in the class with C, that means B is congruent to C. Okay, so by symmetry and transitivity, we get, okay, so what do I mean by that? Right. So I have B is congruent to A and B is congruent to C. So by symmetry, what I'm saying is that can be turned around. You have A to B. A is congruent to B. And then you have A is congruent to B and B is congruent to C. By transitivity, A is congruent to C. Right? So I just wrote the symmetry and by symmetry just to be clear that you have to think of this instead of B congruent to A, you think of it as A is congruent to B, B is congruent to C, so A is congruent to C. That's what we get. Well, and then we're done, hence the class with A is the class with C by theorem 2.3 that we just did. Remember we said if two things are congruent mod N, their classes are the same. And there's our theorem. Okay, so that's a nice result. So if you have two equivalence classes here, two congruence classes, I've probably been saying equivalence class because that's the generic term. So two congruence classes here, they're either exactly the same or they have nothing in common. Okay. Okay, just two more things here. So a corollary here, corollary 2.5, and we're working in congruence mod N. So the first thing it says, if R is the remainder when A is divided by N, then the class with A is the same as the class with R. So think of this R as when I mentioned the division algorithm in the last video, right? That R is referring to that R in that division algorithm. I forgot what letters we used. A is Bn plus BQ plus R, right? Quotient remainder. So this is trying to help you figure out, if you have the class, suppose A is 1,000 and you have the class of 1,000, do you really want to use, that large number? Remember, two classes are related. If two classes are equal, means A and C are congruent mod N. It's so much nicer to use smaller numbers. So if you have the class with 1,000, mod 17, and you typically you want to use a lower number, a smaller number to represent instead of writing 1,000 all the time. So this is telling you, right? How can you figure out, suppose you have 1,000 here and you want to use a smaller number, right? Just find that R, right? So divide by N, use A and N, find the Q and the R, that R will be in the same class as the N. So that'll save you some numbers. And then number 2, there are exactly N distinct congruence classes mod N. Namely, the class with a 0, the class with 1, ... the class with N minus 1. Okay. Now again, you don't have to use these numbers, right? there they are, but what they're doing here is they're using the values of R. Remember in our theorem we had, what was the restriction on R? R could be 0, but R had to be strictly less than n. So for every remainder, 0 to n minus 1, you get a congruence class. That's what this is saying. So this is tying back into that division algorithm. So for every possible remainder you can get, when you divide by n, those turn out to be the congruence classes here. Okay, so we haven't really played with the numbers. We did once. Let's find all congruence classes modulo 4. Now, from the little correlator here, how many congruence classes are there going to be? We're doing it modulo 4, and so there's going to be 4 classes. And this is telling us exactly what they are. 0, 1, 2, and 3. Okay, so we know we have the class with 0, the class with 1, the class with 2, and the class with 3. Okay, so let's figure out what's in the class with 0. Okay. Well, if we go back to the definition, okay, so suppose B is in here. So suppose 0 is congruent to B mod 4. Okay, so I'm trying to figure out what the B's could be. Well, what would this mean? This means 4 divides 0 minus B or B minus, I'm just going to write B minus 0. In other words, 4 divides B. Okay, so what's in the class with 0? It's all the numbers that are a multiple of 4. That's what that tells me. So minus 8, minus 4, 0, 4, 8, dot, dot, dot. Now, if you think about it, going back to what we just said right here, right? All these numbers are divisible by 4, so what's the remainder going to be when you divide by 4? 0, the remainder, right? We're treating these are the remainders. Okay, now what about the class with 1? If we do the same sort of thing, oh, wrong place. So I want 1 to be congruent to B mod 4. That means 4 divides B minus 1. Okay. Well, you know the class with 1 has 1, right? 1 is related to itself, right? It's congruent to itself. We know 1 is in there. Well, what's the next number bigger than 1 that's related to 1? So notice when B is 1, you get 4 divides 0, right? So I need 4 to divide 4. That means B would have to be 5, wouldn't it? And what's the next one going to be? Well, 4 would have to divide 8, so B would be 9. And what about the number less than 1? Because when B is 1, 4 divides 0. So I need 4 to divide negative 4, so B would have to be negative 3. Now, do you see the pattern here in both of these? Once you have one number, how do you get the other numbers? Like here, the class with 0, has 0 in it. Add 4, add another 4, add another 4. Subtract a 4, subtract a 4. The class with 1, has 1 in it. So what do? Add a 4, add a 4, add a 4, subtract a 4, subtract a 4. So if you play this game that we just did, once you get one element in there, the others are just going to be multiples of 4 because we're doing mod 4. Oh, so now with that in mind, how do we do 2? The class with 2 has 2, but then it's going to have 6, 10, dot, dot, dot. And if you subtract 4, you're going to have negative 2, dot, dot, dot. And the class with 3, well, 3 is in the class with 3. And if you add a 4, you get 7. Add a 4, you get 11. Keep going. Subtract a 4, you get negative 1, dot, dot, dot. Now, we believe the theorem here that said if you're in mod 4, there are 4 distinct classes, 0, 1, 2, 3. But look at what we have here. Every integer is in one of the classes, isn't it? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Negative 1, negative 2, negative 3, negative 4, negative 5, negative 6, negative 7, negative 8. Okay, so, we couldn't have another class because we've used up all the integers. Okay, so these are the congruence classes mod 4. If we'd done congruence classes mod 5, there would have been 5 classes, 0, 1, 2, 3, and 4. Okay, so as a definition, very last thing, set of all congruence classes modulo n is denoted Zn. So that's a capital, a big Z. Z sub n. Right, so here, what did we just find? So Z4, it's the 0 class, the 1 class, the 2 class, the 3 class. So it's a set of sets. Right, so Z4 is the set of equivalence classes mod 4. Okay, now one thing I want you to realize here, let me come back to this for a second. Don't mess up your notes, leave it alone. But I want you to realize, couldn't we call this the class with 8? Remember, 0 and 8 are related to, are congruent to one another, so the class with 0 is the class with 8, and this one I could call the class of -3. This one I could call the class of 10. And if I subtract 4, that's -5. This I could call the class with -5. So I could over here say Z4 consists of the class with 8, the class of -3, the class of 10, and the class of -5. That's perfectly fine. That's a true statement. But in practice, just to make things easier, when you say Zn, we represent the classes with the numbers from 0 to n-1. Just, hey, I mean, because if I said the class with 8 and you start subtracting 4s, you're going to hit the 0. That's perfectly fine. But just for consistency, I'm always going to use, if I'm in Zn, I'm going to use 0, 1, all the way out to the class with n-1. Right? Where is the class with n? Right? So 4, this was the class of 4 is here. So the class of 0 is the same as the class with n. It cycles around. Remember when I was counting? 0, 1, 2, 3, 4, right? N is always in the same class with 0. Okay, so that's that section.